Professor Robert Richardson is going to deliver a talk or lecturing on exponential robotics. The session is over to you, sir.
So good morning, everybody. So it's a great pleasure to be here today. So yes, my plan today, I'll talk about exploration robots. And in particular, what I want to do really, it's quite a short session, relatively speaking, is give you a flavour of what can be achieved with robots, and hopefully that'll inspire you to take things forward in the future. So yeah, today, exploration robots is the topic. Okay, so we're technically sorted now. Is the microphone okay at the back? Can you hear me at the back? Is it loud enough? Yeah, good? Fantastic, good stuff. Okay, yeah, so back on track now. So exploration robotics, what's it all about? A bit more about myself for a start. So I did my undergraduate degree in mechatronics and robotics. Mechatronics being the combination of mechanical, electrical and computer science systems together. And of course robotics is a particular form of mechatronics, and robotics typically has autonomy with it. Went to the University of Manchester for a bit, then came back to the University of Leeds. I currently direct quite a few different projects. In particular, my main areas of interest are on robots that are mobile, that can collect data, that can do things in the real world. So not lab-based robots, robots that really can go and do real useful things in the real world. And I guess, as you may know, or you'll certainly find out if you do robotics in the future, there's a big difference between a lab robot and actually a real robot in the real world. So you may not know where Leeds is. I'm from the University of Leeds. Leeds is around about the middle of the UK, and it's about level with Manchester. So you may have heard of Manchester football team. So Leeds is about level with that. So if you are ever in the UK, please do come along and see us. Very welcome to come and see our labs, and we'll talk to you what we're up to in reality, if you like. Last couple of weeks has been quite snowy in the UK, so it's beautiful to be here. Beautiful hot sunshine away from the snow, which is in the UK at the moment. So I'm going to talk today about exploration robots, as you know, but I want to mention briefly what we do else in Leeds. So we have different themes of robotic research, one theme being robotic therapy. So robotic therapy is where you use a robot to recover for an injury you may have. Maybe it's a brain injury or some kind of other injury. So you have a robot device, you use it, over a period of time you recover the lost function and you become well again. So it's a short-term thing to recover you going forward. Another theme which is kind of similar but different is what we call enhansive or assistive robotic systems. In this case you have an injury but you will never recover. So for example, you've lost a leg, you've lost an arm, you'll never recover. So you need a robot device that will help you to do a good quality of life going forward, but you'll always require it in the future. We also have work on robot surgery. So what the aim here is to do surgery on your body, but with the least possible damage to your body. So you don't want to cut big holes in people, making it really small, really precise. And if you can do that, you can have faster recovery. And we also have a theme based upon all other things, so things like AI, so the fundamentals of robotics. So robotics being a systems problem, we have a theme on fundamental side of things. But today is about exploration robotics. So this can be in space, on land, in the air, underwater. Today I'm going to focus much more about land and air, but of course there are similar challenges and similar opportunities, certainly in water, and similar exciting things you can do in space robotics. People often say to me, this is great, you're doing some really interesting things here with exploration robots, but really, is it really important? Why does the world care about you going doing exciting things, finding things? But the fact is that exploration robots can have a really good so-called business case. A business case being it's important for the economy, important for society. So if you look at kind of some of the things, the numbers for robotics are unbelievable. This is in UK pounds. So absolutely amazing amounts of money globally by 2020 will be made by robots. But areas such as agriculture, sorting plants, doing things like that, huge value for things. And if you imagine a field of crops, you want to go and identify 4 or 5 things that are damaged, that's an exploration robot. You don't want to do everything, you want to find these things. So the idea of exploration robots is much more than just going to do, you'll see in here some nice examples of things, but it's much more generally applicable. Likewise in areas such as construction, finding weak points in bridges. Again, it's an exploration type task, very, very useful. So there is a very strong business case, but also a lot of fun, so it's a good place to be. I want to start at the end and show you a video of things we've been doing. Okay, thank you. So I guess it's a teaser, so I will now spend the rest of the time talking a bit about what we're doing here, but that's most of the last year, although some things are a little bit older than that. Before I do that, I want to give you a brief flavour of some of the things that are relevant in robotics, just so you get a bit more of a background about robotics more generally. So, first thing is, what is a robot? So a robot is a system of different parts that work together. Very important, it's a system of parts, and it's not a computer simulation. It must be physical, it must interact in the real world. So here's an example of a robot, actually one of the robots designed by one of our level 4 undergraduate students. So we have a project, we have a module where they design robots. It's one of the robots that I really like. So basically you've got a system, mobile system in this case, it's got wheels. Inside here you've got a battery, you've got a computer, some kind of sensors to go and detect and measure things. And of course the challenge here is for this thing to go around by itself without any human intervention and go and measure things. This one in particular is designed to work actually in mines, so the idea is you're going around mines looking for things, it will drive around there and it'll inspect things. But that gives you a flavour of things. It's very much a systems type approach for robotics. When you design a robot, you really want to design it around a particular problem. So the left hand side here shows you the best way of doing this. So you have a problem, someone says to you, I want to build a robot to inspect crops. You then would go away, you'd do some sketching, work out the shape, the size, how it might work. This is at the moment it's still science fiction. Then you have a stage where you go away and you do some what they call mechatronic design. That is making it reality. Let's add some motors, let's add some sensors, let's work out how we can physically make the structure. And then you build it, of course. The validation is about building the robot, and then you have a solution. So that's kind of the perfect way of making a robot. The reality is, it's just not that simple. So you see here, the right-hand side, this is what really happens. Again, you have your problem, you create some different kinds of conceptual designs, but then you go into the building thing, you build it, it doesn't work, you change it, you keep tweaking it. There's a whole lot of kind of crazy stuff going on here, where you have to have things iterated, tested, that kind of thing. Finally, hopefully, you have a solution that works. So no matter how many years I do this, I aspire to this beautiful, simple, continuous thing. I've made hundreds, if not thousands of robots. I could never do that. I still cannot find a way because there's always things you don't know. You put things together, they interact in strange ways. It's always really hard to do things. So if anyone ever says to you they do robots and they've done a simulation and the simulation is the answer, you know it's not true. You have to do it physically. When you do it physically, you always find things that just really don't work as you expect. In terms of manufacturing a robot, so you've got to design for a robot. I guess you probably, like me, used to think in manufacturing in quite a large scale. So this is like getting things, you cut it with a saw, you hit it with a hammer, you machine it with a machine. Of course, that's a very important part of the manufacturing process. For making things like cars and things, this kind of scale up here, this is what we call like a 10 meter, 1 meter scale, maybe half meter scale, is kind of that kind of scale there. But these days we can manufacture things at many, many different scales. So we can go right down almost to like micrometers, you know, really, really 0.1 millimeter scale, really precise things. So there's opportunity to make robots that are very small that we couldn't make before. So when you're doing your design process, think about the manufacturing, and maybe you'll be using lasers, chemical etching, all kinds of different techniques to manufacture things that aren't the conventional, get a bit of metal, let's cut some holes in it. So it's a different kind of thing for designing robots. Of course, your robot has to move, do something physical. To make it move, you would have some kind of motors, for example, electric motors. I guess you're familiar with what these are. There are not many things. So you give some voltage to it and it spins around. There are different types. I'll just briefly mention how they work. And the first one is called a brushed DC motor. So in this case, you have bits of material that are magnetic. You have wires that are electrical. When you put electrical current through the wires, it creates a magnetic field. As you know, two magnets oppose, you get an opposing force, and in doing that you get some kind of repulsion or a rotation. So in this case, you give it a voltage, it starts to rotate. When you get beyond a certain point, you'll get a balance or an equilibrium. You have to reverse the direction of the voltage to keep it spinning around. So you'll see here, you have this kind of half bit here. As it spins around, at a certain point, the actual signal will reverse, thereby creating a continuous thing going on. This is nice, simple, cheap. You get a battery, you put it on, it just works with a battery. The downside is that you have these things called brushes. In order to maintain the electrical signal to a rotating part, you have to have a brush, like a floor brush, that's constantly doing it. It works fine, but you get wear, and you also create sparks. So there are issues if you have robots working in combustible environments, you wouldn't do this because it would combust, it would create sparks, which is not good. Likewise, a different way of doing it is what we call a brushless DC motor. In this case, working on a very similar principle, the difference being that rather than having this thing where you have these brushes that touch, you have different coils around the outside, and in the center you have a permanent magnet. And what happens is, when you energize these coils, you get attraction. So initially you energize this coil, and the north will rotate here, then this coil will rotate here. So by a series of pulses, you can cause a rotation. And that's simple, and the good thing about this is you have no mechanical contact, there's no brushes, less wear, no cause of sparks. It's really quite useful. The downside of this is that you can no longer get a battery and just attach it. You have to have an electric circuit that makes these things pulse in sequence. So quite useful, but difficult to control. But they are generally used in very high power applications. So all of the drones, for example, you'll see flying around, they're all using brushless DC motors, whereas most of the ground robots tend to use brushed DC motors to do with weight, power, density, that kind of thing. Of course, you use gears to change the force, the speed of the things, to make it faster or slower, and higher torque depending upon what you want to do. In terms of moving, you can have things with wheels. So in this case here, a very simple lab-based robot with two powered wheels and these casters here. This one is effectively this one here. You could have different combinations of them. Some of the wheels can be powered and steered. You can have tank tracks. So these views here are from underneath, looking at it upside down from the top if you like. Different configurations of wheels have different benefits, different kind of qualities. Or you can have legs. We can use legs. We can make all kinds of complicated things with legs, with joints. In this case we have a kind of a spider here. We can try and simplify the numbers of degrees of freedom. So one of the things about robots is you really want the least possible number of joints. Every joint is cost, energy cost, and also things that can go wrong. So the least joints possible is what you want. But in certain scenarios you can have legged robots. And of course, you can go right up to humanoid robots. We've seen them, I guess, on TV and films and things like that. You can build robots that are on 2 legs that are like humans, but in this case here, a very simplified human. It has 47 what they call degrees of freedom. That's 47 different types of movement, different movement directions. Hugely complex, hugely expensive to control, to use, to build, to make. Very, very difficult. So you'd only ever really have this in a useful case when it's worthwhile. So you see lots of examples of these things. They're mostly demonstrations. And I guess you haven't seen an example of a humanoid robot doing a useful task where the investment is actually worth the actual what the robot's doing. It doesn't exist. They walk around, they look great. What can they do that justifies the £1 million UK price tag? These days, not enough. So it's a question of development for aspirational reasons rather than right now for useful, on-the-ground things that it can do. Of course, batteries are very important. In fact, batteries are one of the things that have caused robots to be really useful in the last, say, 5 years. Batteries means that robots can operate by themselves without wires for much longer periods of time. We know that these lithium and polymer batteries, like in our mobile phones, are really useful, really powerful. This is being driven very much by the autonomous car industry or electric car industry. Big batteries for cars, massive, massive big business. And the robotics industry can benefit from this and potentially have robots that operate for days or even weeks without requiring a recharge. That's a massive, really game changer. So right now, drones flying maybe half an hour, flying around, these are rotary drones. Potentially in the future, they could fly for days. So massive, massive game changer in battery technology. Of course, as you go around, you need to move, but also sense. If you can't sense what's going on, you can't do anything. Loads and loads of different sensors. We won't go into detail of them here, but we must be able to measure what's going on. Are there gases? Is there light? Is there heat? These sensors help us to work out how we're going to move and how the robot can make choices about what it does. And likewise, in terms of measuring things, this is an example of a two-dimensional top view of a building. You could laser scan them, very expensive things, maybe even 100,000 UK pounds to actually laser scan something, very, very expensive. You can use very simple sonar sensors, but the quality of the sensor depends upon the quality of the measurement, as you might expect. So for example, using these sonar sensors, they work by sending out a beam of sound, send some sound out, wait for the reflection. By measuring the time of flight, you can work out what's there. But you have problems with these, you have these kind of weird reflections. So I could send some sound out this way, I could measure the reflection, but I might also get some sound back bouncing around the room, coming back from different directions. So you get error. And this is an example of a sonar scanned room. So rather than it being a lovely, crisp, nicely defined shape, you have all these kind of strange effects. So these effects here are where you've mismeasured things. The sound's gone out, somehow you've had a signal back, and the robot thinks that it's measured a certain thing being solid, but it hasn't done. So definitely a compromise there, cost and usefulness for the robot. Of course, mobile phone cameras are amazing. We know cameras are amazing. There are still big challenges around using cameras for robot vision. For example, what you really want to do is take this kind of photograph and work out what's there. It's really difficult, really can't be done. So even this simple scenario here of working out what's a door, what's an obstacle, very, very hard to do for robots. We know that if you have an apple on a desk with a good lighting condition, you can use some kind of new deep learning stuff and probably say, okay, it's an apple. Google do it all the time on their web searches. That's a really defined scenario. It's very hard when you've got different light levels, you've got multiple objects in the same picture, so there is still big challenges around the vision. We are getting better, and maybe at some point we'll get better in doing that. Of course, we want robots to go and do things by themselves, make decisions. So you have this thing called the sense, think, act cycle. This is all about, or mostly used in industrial applications. So you do a sense, you measure something, then you do a series of things, you measure it, what should I do now, and then you go through and then you do the action. So it's a sense to action. It works really well in a very simple environment like a factory where you have only a set number of things that can happen. It's very simple, very guaranteed. It's very bad if you have a very complicated scenario. Many things can happen, very hard to do. So you have other ways of doing this. So rather than being a single thing, you have what we call a behavior-based approach. In this case, you have many, many different things that it can do, It takes a measurement, and based upon the measurement, it decides what action to do. So there's not one thing it might do, there are multiple things that it could do. So for example, in this case here, you might have avoid things, hand somebody a cup of tea, many different choices it can make, and based upon what it senses, it chooses one of the things to do. And you can prioritize, you can have some things that are more important, like don't fall downstairs, obviously it's more important than be friendly, potentially. The problem with this, though, is that it's very hard to be sure what it will do. So if you're in a nuclear factory or nuclear power station, this kind of approach is quite dangerous because it's very hard to be sure for a particular set of sensor inputs exactly what it will do. And for a safety critical case, you just can't have it making any mistakes. So the first thing I showed you is defined, rigid, you can guarantee mathematically what it will do. This is much more difficult. So there are definitely balances there. This is used, for example, in robot vacuum cleaners. That kind of thing where if you make a mistake, well, you bump the skirting board or you bump the wall. That's okay. It's not used in critical applications where you've got to be careful about things going forward. We've talked about autonomy being a robot making its own choice. But the thing here, I guess, is very important is autonomy is not yes or no. There are levels of autonomy, so levels of independence for the robot. So let's go down the bottom here. We'll start at number 1. So you've got a radio-controlled car. You're driving it. That's the level 1. There is no computer helping you. Whatever you say, it does. It still has motors, has electronics, has communications, but it's you. It's all about you. There's nothing else going on. Level 1, autonomy. As we go up, we get more and more input from the robot, from the computer. So for example, level 5, we're now halfway up the autonomous scale, if you like. Now what is going to happen is the actual robot's going to say to you, I think I should go and clean that window. And it's decided to ask you the question, you say yes or no, and then it will go and do it. So it's very much getting towards autonomous, but still it's asking you, I want to do this, is that a good thing to do? So you're still in control, but the detail of exactly how it does things is done by the robot. Let's carry on going. Let's go up to number 8. So number 8 is getting very much towards this kind of really high autonomy level. So now a robot's in your college, for example, it'll do whatever it wants, but if you ask it what it's doing, it'll tell you. So it'll interact with you. You can say, hey, what are you doing? And it'll let you know. That's really useful. So it communicates, but it works completely independently. It's not asking permission, but it will tell you what it's doing. As we go up, we get even more kind of scary sort of things, I guess. So on number 9, now the robot will tell you what it's doing only if it wants to. You can't say to it what you're doing, or say, none of your business. I'm not going to tell you. So only if it decides to do so, it will tell you what it's doing. That's obviously quite risky. And number 10, I think we never want number 10. Number 10 is a completely autonomous robot. It will never talk to you, never tell you what it's doing, just do whatever it wants, and you'll have no control. That's effectively full autonomy. I guess it's like a person in that sense, it has full autonomy. We don't want that. So we're really looking, I guess, somewhere down about 7, 6. So when people talk about autonomous robots, there is definitely a limit we want to go for, and the full autonomy is not something we should ever, there's no reason why we want to do that. It doesn't make any sense to do that. This brings us on to quite an interesting question about what should robots do ethically. So we have what we call the principles of robotics. So what should they do philosophically, if you like? The first one's quite sensible. Robots should not be designed purely to kill people. That's really not a good thing to do. We don't want to do that ideally, so we shouldn't do that. Another one here is interesting. So it's always going to be that humans are responsible for what robots do. You can't say it's the robot's fault, nothing to do with me. Humans are always going to be responsible for what a robot does. That's quite important. If we go down, level 4, this one down here is quite interesting. So there are lots of work right now being done for robots to help the elderly. Maybe they've got some brain problems, maybe they're quite frail. You have these things you can buy like robot seals, robot dogs, and they give the people reassurance. You can stroke them. So I've held some of these things in my hands, and they're great. You hold them, they're nice and warm. You stroke them, they move. They're like animals. It feels really good. But the important thing here is we should never fool somebody into thinking it's a real animal. It should always be obvious that the robot is a robot. This gets quite difficult. So for us, it's quite easy. You say, okay, it's a robot. We know that, we've been told. But if you're using it for somebody with a brain injury who perhaps is quite vulnerable, how do we be sure that that person understands it's a robot and they're not fooled into doing things? I mean, I guess the example of a robot dog is quite simple. You can imagine worst case scenarios where we have fully robot people, and that could be really serious, so we have to be careful about that sort of thing. And the last one on here is very important. It's something that the automotive industry is doing right now for autonomous cars. It should always be possible to work out legally who is responsible for a robot. So have a robotic car, it drives down the street, it drives into your house, not in a bad way, through your wall. You need to be able to prove whose fault is it. Bear in mind it's an autonomous car, so the person sitting in the back of the car had no control. Is it their fault? Is it the person who bought the car? Is it the person who built the car? Is it the person who made the software for the car? But very importantly, it must always be legally possible to find out who's responsible. And that's tough though, because there are examples, for example, for the autonomous car. It's driving down a street, a child walks out. The car knows it can't stop in time to avoid that person. Does the car decide to drive into the building, injuring the passengers of the car, or does it drive and hit the child? Really difficult scenarios. Of course, humans face it all the time. We face it, we make the best choice we can make. There's a no-win scenario. But if you're in a car, you own the car, and it chooses to drive into a wall and injures you badly, do you want to buy that car? It's quite an interesting scenario there. So, but anyway, lots of work going on these sort of things here, the principles of robotics, which are very important. So that's the end of my quick flavour of robotics. Hopefully I've given you a flavour of what's going on. And now we'll talk about particular things we're doing in application domains for robotics. So for exploration, we tend to classify these in the different types of things you're exploring. So it could be an open space. Very large open space has different challenges to things where you have kind of smaller things. So open space is much more about the size of the space, energy power, that kind of thing. So we're doing some work looking at ground robots, but in particular, how can you make ground robots be able to explore a space quite efficiently? So driving around, using a camera to inspect things. So we developed a new kind of robot, or a new kind of robot locomotion. In this case, we have 6 wheels. These wheels are joined together by a central axle, and they've got a rotation point. We've got a rotation point on the center point here. So each one of these things can spin around in different directions. The good thing about this is a normal car, you drive forward, you steer. As you know, when you park your car, you have to kind of steer backwards and forwards. This car, or this vehicle, can go sideways, it can drive in squares. Let's have a look what it can do. You can drive in all kinds of different ways, which is unusual. So you can see here what it's doing, these things are spinning around. The actual rotation point here has no motor. That spinning is caused by the 2 side wheels moving in different directions. So if these 2 side wheels go the same direction, you go forward. If these 2 wheels here go in different directions, it spins it around, so you can control the speed of that. So right now we're driving as a conventional car, just driving around different directions. So of course you can go forward and backwards, very similar, very straightforward things. I guess note here that these actual wheels, the centre point is free to rotate, so it's holding that angle by careful control of the speed of these 2 wheels. So that angle there, nothing holding it, it's a free to rotate centre point. It's the wheels that are keeping that angle locked on by some measurement and feedback control. So it gets more fun now, so we can do things like spin on the spot. So we can now spin fully on the spot, we can do a scan rotating around. So this camera here is going to inspect something. What is really nice, if the camera can point at the same thing as you drive around, it makes it much easier computationally. So you can have the things where you're going to mathematically work out what it's seeing, but ideally you'd point in one direction. So what's happening here, the robot's driving in different directions, this camera is always going in the same direction. That's great, so you can now drive in squares, you can drive in weird circles, things you couldn't normally do, you can do with this kind of technology. So this example here, you can see we've done kind of squares. You can do also much more complicated things than that. So in this case here, this is the triangle of the robot. You can cause the triangle to drive in a curve whilst the box spins around in funny directions. So it can be really kind of a coupling of forward and rotation. This one here, another example here. So it starts off being the triangle being here. You could drive forward. As you drive forward, the actual top box can spin around. So you could do all kinds of weird things that perhaps not that useful, but certainly interesting to look at. That's one example of a ground robot that can do things. We also have work looking actually at mapping of glacial melt lakes, surface water. So the question really here is, how can you work out how much water is on a glacial melt lake? So that means basically it's a lake somewhere that's cold that may freeze or may melt. So it depends, the actual size of the lake varies throughout the year. The reason they're asking this question is they want to know how much water. So water is effectively energy, conversion from ice to water. If you know how much water, then you can do things and work out the energy in the lake and that sort of thing. So that's a challenge right here. The lakes that are quite big, normally you can drive to with a truck, get out a boat, you can row around and you can measure the depth. So if you have a satellite photograph, you know the top area, how big the area is. What you don't know is the volume, how much water. You can guess. We could all go, oh, that's obvious. You know, you've got a circle, obvious what the actual volume will be. But you have to be sure. It's a science here, it's not kind of a guesswork. So you have to be sure what the correlation is between the area and the volume.